group. Marcel, if you could go ahead and start sharing your slides from now. Marcel Green is a math major who is, a fun fact about him is that he has 3 young rescue dogs who added joyful chaos to his daily life. Marcel was mentored by Sergio Cordero as part of the Stanford X Lab, and he will be presenting developing a carbon dioxide sensor for deployment in extreme environments.
Good afternoon, everyone. My name is Marcel, and I'm excited to present today on the development of a carbon dioxide center for deployment in extreme environments. This was a remote internship made possible by Stanford's X Lab, as well as through the work of my mentor, Sergio Cordero. Before I dive into my internship, I wanted to discuss the big picture, global warming. Carbon dioxide, or CO2, causes climate change by trapping heat and contributes to respiratory disease in the form of smog and air pollution. In addition, it raises the acidity of our oceans. So how do we tackle this unavoidable issue? Carbon capture and storage. Following along with the graphic shown below, as industries release this gas, they capture and compress it before injecting it into geologic formations, where the rock seals the CO2 and prevents further emission. However, there are weaknesses in this system that require advancement. The pipeline shown here that ruptured in Mississippi put hundreds of lives at risk, and authorities lack the technology to properly respond in a timely fashion. This event highlights the need for the focus of my internship, which are chemical sensors that can withstand these environments and provide data for risk mitigation. My main focus for this internship was to identify nanomaterials for carbon dioxide sensing in extreme environments and optimize lab testing through the enhanced remote programming of those materials. However, in order to properly integrate carbon dioxide chemical sensors into the carbon storage process, I had to identify the right combination of materials that followed in accordance with the extreme storage conditions you see on this slide. The 2 main materials advanced for this project are metal organic frameworks, MOFs, and aluminum gallium nitride, a heterostructure. Metal organic frameworks, or MOFs, are composed of metal ions linked by organic molecules and can be used to enhance the sensing capabilities of sensors for CO2 detection. MOFs provide a large surface area for CO2 absorption, which combine with the aluminum gallium nitride's high sensitivity. Together, they enable the development of highly sensitive and selective CO2 sensors. This slide is a display of the timeline of my work for this internship. I started with a literature review utilizing keywords to specifically find articles related to my research focus. I was able to use Foothill's digital library to access academic databases such as JSTOR and ScienceDirect. From this point, I moved to parameter development, implementing the research data from my review. Next, I selected the ideal materials in the form of the specific metal organic frameworks I wanted to utilize. I then transitioned to integration with the aluminum gallium nitride platform, and lastly, experimental application. For the final 2 steps, we were able to utilize the Raspberry Pi, which is a microcomputer that I was able to remotely operate using the application TeamViewer, which is a remote control computer software that granted me remote access to the X Lab. Combining these materials, I utilized the programming language of Python to write commands to assist. This is my literature review. This grid compiled all of the research data and sources, as well as relevant scientific articles that I examined. As you can see here, there are over 90,000 metal organic frameworks that are currently in existence, and that number continues to grow as more and more are synthesized and manufactured. I needed to utilize the data provided from previous research, and my project goal was to select the best nanomaterials available. So in order to do so, I was able to create this table with the desired parameters required for the sensor for the best possible success. I was then able to determine that ZIF-8 and MIL-101 were the 2 best candidates due to their unique capabilities that align with the goals of this project. The qualities you see listed here make each of them effective elements of chemical sensors for monitoring potential leaks such as the one shown in Mississippi. This is the current setup at Stanford's X Lab for the testing of these nanomaterials, where carbon dioxide and dry air are controlled in the tank shown at the far left. The flow of gas is dictated by the 3 flow controllers you see here, with the control at the bottom implementing humidity through the bubbler, before entering the calibration and linkum chambers, which allow for further study of the sensor itself. My second contribution to this internship came in the form of drafting Python code, in which I worked to develop the script that allowed for the synchronized control of all 3 pathways highlighted. The goal was to allow lab members to input values remotely and alter the parameters as they wish to truly fully test these materials. This form of testing could now hopefully include the simultaneous manipulation of values of relative humidity, carbon dioxide concentration, and flow rate. The code implemented would also be able to minimize error and allow for materials to be tested as extremely as possible or as needed. As an active duty service member, I became keenly interested in the benefits of sensors in extreme environments, as chemical, biological, and radiologic warfare can endanger the lives of operators. In addition, as seen in the events that occurred in Mississippi, as excited as I am for this technology to be implemented, I also came to the understanding that we need to take time and care on the development of not only these sensors, but our approach to climate change technology. Lastly, I wanted to especially thank my mentor, Sergio, for being extremely flexible with my active duty schedule, as well as my mentors of Marissa and Sophia for working with me through all the time changes, as well as Stanford's X Lab and Foothill College for this opportunity. Thank you.